So yes, I'm going to talk about integrability and how integrability, how we can learn about AdS CFT using integrability. But before I start, let me start with this question, which I'm interested in answering. Probably many of you here are also interested in answering this question, which is how does the worldsheet emerge from large N gate theory? So this question is important. Well, it will be very nice if we can answer it. But in order to explain what I really mean by this, let me just add some comments. So ideally, what I personally want to understand is to find some method or a way to reformulate for any given large N gate theory or a large N series and find some like a systematic, presumably universal, hopefully universal and systematic way rewriting and which converts large N gate theory into some 2D worldsheet theory.
Do you mean string theory, or you just mean some two-dimensional field theory, or what?
Okay. Yeah, nice question. Well, I mean 2D string theory.
String theory.
String theory. So like I'm talking about some large N gate theory which are joined.
Two-dimensional conformal field theory.
Right. Two-dimensional conformal field theory. Yeah. So that's like a very ambitious goal, as you can imagine. And
you expect to see the conformal field theory or the gauge fixed?
Okay, that's also a good question. Let me say, for now I'm happy with just gauge fixed description. So this is something I would like to achieve, maybe in the future. Well,
that would be the improvement on what Toft did.
Yes, so Toft already showed like some qualitative understanding between the large N like two diagrams and the two-dimensional surfaces, like a theory living on the two-dimensional surfaces. But we still don't have a systematic way of deriving what theory is living on those two-dimensional surfaces. Of course, so this is great if we can achieve. And of course, like if you take any like a generic large N gate series, then probably this 2D theory is also complicated. But still, we expect, because it's a 2D theory, maybe it's easier to solve. Well, it might not be like a solvable or integrable models, but still, like if it's 2D series, then certainly it's probably easier to analyze 2D series rather than large N gate series. So this is a kind of question that probably one wants to achieve. But I should say that we are quite far from achieving this goal. Like,
is the hope that you can, like, just from the Lagrangian of the field theory, find the Lagrangian of the 2D theory without actually solving?
Yes. So that's what I mean by this. Like, find a way of rewriting, like starting from Lagrangian to find some Lagrangian, or maybe find my roots to Lagrangian.
Right. So you may not be able to solve either.
Right.
Relate to problems.
Right. So, but I should say, like, we are quite far from it. And we don't, at this moment, we don't have a concrete, let's say, interacting example. Of course, like for free series, there is important exception, which is AdS 3 times S 3 times T4, worked out by Rajesh and Matthias. And then also AdS, there is a recent proposal about AdS 5 times S5. But those are free series, and in the interacting example, we don't quite have a concrete solvable concrete example in which we can achieve this. And I should emphasize that this is true even in, for example, in old matrix model duality, by which I mean duality between double-scaled matrix model versus like a non-critical string like minimal string. So in those examples, we know minimal string. We know what both sides are. So like this side is just like a one particular limit of some matrix integral, and this side is basically string theory whose worksheet theory is composed of minimal model and a dual theory. However, we don't have a systematic way of converting these matrix degrees of freedom into the 2, p, for example, 2, p minimal string.
And even if you did, it wouldn't. I mean, the matrix model is basically a free theory, right?
Well,
You consider
yeah.
the double scaled one you go to.
Yeah, double scale one, like you need some potential term. And
Theory of free fermions or.
okay, in the sense of free frame, it's free theory, yes. So yeah, but that's a good point. And in these models, we can actually solve both sides, but we still don't completely solve the both sides. But we still don't know how to systematically like convert one to the other.
It's basically the leg pole factors, right? So, meaning we have a continuum variable on the matrix side,
Right.
which is like the density of the fermions.
That's true.
We have a continuum variable on the bulk side, which is like the tachyon, and we know the relationship between the two, which is this leg pole factor, but we don't know why that's the correct.
Okay.
Is this what you're saying?
Okay, but I think like a density of fermion is closer to like a field theory in terms of density of fermions, actually closer to string field theory rather than string worksheet theory. And here I'm talking about slightly different, like a rewriting, like a deriving the string worksheet theory.
I see.
Deriving the string field theory in this context is probably hopeless. Like in higher dimensional field theory is complex, hopeless. So the modest goal here, especially
I understand.
theory, is to derive 2D worksheet theory.
Sorry, and just about that, in the old days, not that I'm very familiar, but in the old days there was the story of how these matrix models discretize that string world sheet.
Yes.
Is that not more or less a derivation of the string world sheet theory?
Right. So there is some intuition like how this like a worksheet gets discretized because of the double scale matrix model, but I guess like a precise derivation of like for example.
It was pretty precise, right? I mean, you go to this double scaling point, the number of vertices becomes infinite, the discretization becomes almost continuum. I don't know the story as well as some people will, but that sounded almost like a derivation to me.
Yeah, it's not you have a picture. I think the picture is there, but it's not a way in which you derive the field theory living on that Riemann surface.
Identify the measure of the integral on the continuum.
Not
theory?
in any precise way, I think.
Yeah, I think it's not. Yeah, it's not very precise. And one difficulty here is that actually like a deriving Lagrangian here is hard because like it involves minimal model, which is not Lagrangian. So in that sense, like this problem is actually like a bound to be hard. Maybe like actually in recent recent story of like a JT gravity matrix model might be actually a good target for this question, because if you take certain limit of the double scaled matrix model, then we know that it's going to be due to JT gravity living on the worksheet. And this JT gravity has a very simple action. So in this context, it might be actually possible to derive this relation. But even in this context, we haven't been able to like systematically derive the JT gravity degrees of freedom out of the matrices.
What about C equals 1? That sounds even simpler.
Okay, C equal 1 indeed. C equal 1 is a good point. That's a good point. But still, like, yeah, that's another nice target, I agree.
I don't know why you need a Lagrangian for the string theory side. I mean, you just need OPEs, you don't need a Lagrangian.
Okay. That's true.
So you need Feynman rules on the left-hand side.
Right. Yeah. But okay. So let me just say one comment to the Nathan's question. So So if you compute something on this side, then what you get naturally is the integrated correlators on the worksheet. It's not necessarily easy to read off the OPE of the worksheet. Okay, so let me end with blah 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 and and then come back to integrability. So with this motivation in mind, let me just motivate you why or what's interesting about the integrability approach to n equals 4 Super-Mills theory. So the integrability approach does not answer this question, but it gives us some feeling of how this could potentially work. So let me just say a few words what I really mean by this. So the integrability approach to n equals 4 Super-Mills, as I'm going to explain, combines, so this method allows us to combine intuitions coming from both gauge theory and also from string theory, string worksheet theory, and it combines them into a single computational framework. So the fact that integrability approach works is already computational framework, suggesting that there is something that nicely interpolates the gauge theory picture and the string theory picture. So the hope is that by understanding the integrability approach better, maybe we learn how we can achieve this goal. So this is one possible way of motivating integrability approach.
Shata, one more sort of general question before.
Yes.
If we look at AdS 3 times S3 times D4 for a moment, there's this place where the worldsheet theory is purely NS-NS. But that is precisely a place where the where the field theory is sort of singular, because you have these long strings, right? So it seems to me, and maybe this is wrong, but it seems to me that in every example that we have a non-singular, apart from k equals 1, where the singularity goes away, but almost every example where we have a non-singular field theory, the dual always involves Ramond-Ramond fields. Now I was wondering whether this was somehow just bad luck, or you think it's somehow important that the Ramond-Ramond fields play an important part in making the duals to field theories. It's a vague question, but I mean, it would have been nice if we could find just an NS-NS background, right? Because we're most familiar with those. But somehow it never seems to work.
But I mean, why do you say the field theory is singular? I mean, it's maybe a little bit complicated, but it's not. It's a non-compact CFT, but it's not. I mean, it's probably still a fine 2D CFT. I mean, it's sort of complication of sort of Liouville type, but it's not. I mean, it's more the symmetric orbifold of Liouville types.
Okay, but singular in the sense that elliptic genera could jump at this point and so on, right? Because it has a continuum coming down, even though.
Well, to go from k equals to 1 to that, elliptic genera can jump, but afterwards they probably stay the same.
I agree. So once there's this point where you have this new continuum, right?
Right. But that continuum by itself is a CFT. Okay, it's not a rational CFT, but it's not more crazy than many CFTs you'll encounter in your life, like Liouville.
And it's almost rational.
I mean, it's not too bad.
Okay, but in the whole moduli space of AdS3 compact, AdS3 times S3 times D4 compactifications, there are very special points where you get these long string tubes. And where you have this description lies exactly on them. Right? So to move away from this non-generic behavior needs turning on Ramond-Ramond flux. And that's precisely what we don't easily know how to do.
Right.
So I was wondering whether somehow it was more than a technical thing. It's such a vague question, maybe we can go on with it, just in case anyone has a comment.
I mean, the minimal string theories are also, I think, I mean, they are maybe very simple, but they are non-trivial examples of this duality, but without
Ramond-Ramond.
Without Ramond-Ramond.
Yeah, indeed.
So I don't see an in principle reason, but.
But, you know,
And look, we don't know what these other worldsheet theories will really look like.
that's what I meant. I was wondering whether the
I mean, maybe they are so complicated that they are beyond the sort of realm of
Yeah.
CFTs we are familiar with.
That's what I meant. I was wondering whether there might be structurally new elements in the worldsheet theories, dual to field theories, that we don't think about because we're most familiar with these.
Right.
Most of us are most familiar with these Ramon-Ramon, having non-Ramon-Ramon backgrounds.
Yeah, I don't think that, I mean, you obviously need fermionic coordinates, I guess these matrix models don't have, but other than that.
Just, okay.
Yeah. I mean, if you generally just think of string backgrounds, it's probably non-generic not to have them Ramon-Ramon flux. If the generic background, I mean, in the landscape of all string theories, you would generically have Ramon-Ramon. So in that
It's
sense,
not a surprise, yes.
in that sense, perhaps it would be, understandable that an arbitrary gauge theory might have Ramon-Ramon.
Maybe the thing that's bothering Shiraz is it's not an n equals 1, 1 superconformal field theory. If that's your definition of string theory, then you're right, then it's not a string theory. I mean,
Your pure spinner is not an n equals.
it's not an n equals 1, 1 worldsheet superconformal field theory.
Right.
If you try to define it that way, instead of as a just two-dimensional conformal field theory, then
Okay. Good. Okay. Good. That's interesting. Thank you.
Okay, so let me just go on. So this motivation, like so I plan to say something about spectrum and then correlation functions. So the first part is just to like I said, the stage and review the basic facts about integrability approach. And then I'm going to say something about correlation functions, which is based on hexagon formal, what's called hexagon formalism. And if the time permits, probably not, but I might say something about quantum spectral curve as well. So this is the plan. So let's start with the spectrum part. So this part, especially the first part, might be boring to many of you, but because there are also some students, young people. So let me just briefly review what we mean by solving n equals 4 supermills by integrability. So this was initiated by a seminal paper by Minahan and Zarempo back in 2002. Actually, this is already 20 years ago. And so what they did is to study some...
We're getting old.
to study some anomalous dimension, one loop anomalous dimension of some composite operator in n equals 4 supermills, which for simplicity, let's consider some simple class of composite operator, which are made out of like two complex scalars. So z and y are two complex scalars, which are in the adjoint representation of the gauge group. So you just multiply them several times and then take a trace. You can define the gauge invariant local operator. So importantly, all of these fields are at the same point in this space-time. And what they found is that, okay, so they basically just did the honest perturbative analysis of computing one loop anomalous dimension, dilatation, like computing the conformal dimension. And what they found is interesting. So once you map this zy, zz's into some spin chain like state, so map z to upspin and y to downspin, and then they found that the action of the one loop dilatation operator, whose eigenvalue gives you the anomalous dimension of this composite operator, can be mapped to a very simple Hamiltonian of the spin chain, which is what's called Heisenberg spin chain. So this is just the usual SU2 generators, which act on up and down basis. And importantly, this is the nearest neighbor, and the reason why it's nearest neighbor is coming from the planarity. So if you have like a bunch of z and y's, and so these are like a double line notations, and then if you try to like draw gluon exchange diagram, so this kind of diagram is allowed in the leading large n limit, but if you try to connect non-nearest neighbor lines, then this becomes non-planar diagram, so it's suppressed. So because of, and that is basically the reason the resulting Hamiltonian is like the nearest neighbor spin chain. And what was amazing about this discovery is that this nearest neighbor spin chain can be solved exactly using a method called beta ansatz. So let me just say that this anomalous dimension just corresponds to energy of this Hamiltonian, so the problem reduces to the diagonalizing this Hamiltonian. And people in condensed matter basically, or statistical mechanics or mathematical physics, basically developed a method to compute and diagonalize this Hamiltonian of the spin chain that goes under the name of the beta ansatz. But let me just, I'm not going to explain how to derive the beta ansatz, but I'm just going to show the final answer that determines the energy spectrum. So the beta ansatz consists, in order to solve this equation by beta ansatz, you first need to solve this what's called beta equation. Where in this case E2 I T U is some function of u plus I over 2 minus over u minus I over 2, and S u v is u minus v minus I over u minus v plus I. So you basically impose this condition for all uk. So this is the we have this equation for each k. So this is a product over j not equal to k, and so this determines by solving by using this expression. This gives some algebraic equation determining the values of uk, and once you determine the values of uk, then you can compute the energy using this expression.
So the UKs are the length, there are L of them, and this is an equation for this.
Right, so yes, thank you. So
L equations, and then we solve the UKs from that.
yes, so okay, so let me just say. So I didn't as Fernando was asking, I didn't explain what these UKs are. So these UKs, you can think of it as a kind of like a label, which labels the different energy eigenstate, and it's basically a set of m complex parameters, and this m, m can be anything, m as long as m is smaller than L over 2 in this case, where L is the length of the single trace operator, or in the spin chain language, it's the length of the spin chain. And yes,
The UKs are not real.
UKs are not real, not
So
necessarily.
why is the energy real? Or is it?
Oh, the energy is real because this equation is invariant under the complex conjugation.
Mm.
So if you have a complex UK, there is always a complex conjugate, and then if you sum it up, then you get a real number.
So any solution to that equation has the property that the solution is invariant under complex conjugation?
Yeah.
So you're saying m can be any number smaller than L? So that means you're sort of ignoring some of the sides of the spin chain, or how should I think about this?
Oh,
You would have many solutions, right? One with m equals 1, one with m equals 2,
Yes.
m equals 3,
right.
and all these are states.
So these are the number of holes, or
something.
No, number of magnets. Yes. Number of magnets. I'm going to. Yes. Yes, I need to write a physical interpretation. So I said like this is just. Here I just said like this is some abstract label, but there is more physical way of describing what this number m is. So the physical meaning and also physical interpretation of what this equation is. So the physical interpretation is that, so if you want to construct so let's say we have like a spin chain, and one way to construct the eigenstate, especially the eigenstate of this Hamiltonian, is to start from the ground state in which all spins are up. And you can easily check that if all spins are up, that's an eigenstate of this Hamiltonian. And then you start describing other eigenstate by flipping some upspin to downspin. And the number of downspin is precisely what corresponds to m. And this UK basically has an interpretation as the momentum of case downspin. So the way data ansatz works is to write down the ansatz for the wave function, which is basically a product of like a bunch of plane waves plus some extra factor coming from this matrix, and then impose that the ansatz wave function is really an eigenstate of the Hamiltonian. And if you solve that equation, if you impose that equation, you can actually derive these two conditions.
So that S is actually an S matrix?
Yeah, that is actually S matrix. And then like the final equation that you got from here has a very nice physical interpretation, because this is just a propagation factor when one magnon goes around the loop, the chain, whereas this is the scattering between magnons. So maybe I didn't introduce the word magnon, but this excitation people often call magnon, because it's kind of excitation on the spin chain. So
U is P of U is not the momentum. U is the momentum.
Sorry. Yes, P of U is the momentum. Yes, and U is just like a nice way of labeling the momentum.
And the fact that P of U is also not real. So
right.
So I guess these are unstable.
So they are interpreted as some kind of bound state of two magnons. Okay, so what I just said about this equation is that, so this data ansatz equation can be understood as a condition that the total phase shift of the magnon when it moves around the chain is just 1. So then the phase shift comes from two parts. One is just a simple propagation factor, which is E to IPL, and also the scattering phase shift.
So this S matrix is the same whether a downspin goes past the upspin or a downspin, or?
So the S matrix is non-zero only for the scattering between downspin and downspin, because when we describe this system from this picture, upspin is just a kind of ground state, so we view it as nothing. It's more like a field theoretical interpretation. Okay.
Sorry, and this equation is exact for all L only when L is large compared to the number of magnons?
So at this order, this is exact for all L. And if you want to, if we start generalizing to finite coupling, then like this equation is exact only for large L. I'm going to get to that. So this was the result.
At one loop there are only planar diagrams, or why don't you need planarity? I mean, this is one loop, right?
This is one loop.
Are you saying at one loop all diagrams are planar? Or?
No. Well, there are also non-planar diagrams at one loop. Sorry, I'm not understanding the question.
I mean, you're saying that you're not using large N here. So I thought large N means you're
Large L.
Large L, yes.
Sorry.
Okay, so what I said above here is a kind of result at one loop in the planar limit for this particular class of operator, which are made out of like two complex scalars. But people found that this can be generalizable at one loop to arbitrarily single trace operators. And so arbitrary single trace operator, let me just write an example. In addition to y, we might have some fermions inside, or we might have some covariant derivatives inside z, and of course we can also have some other scalars like x, y, and z. So all these like extra insertions, which are not z's, are regarded as some kind of like excitation. So the new ingredient here is that previously, when I was considering this particular sector, there was only one like a species of magnons, but now we have several species of magnons. So, and in order to deal with this like different species of magnons, it's nice to introduce some like a definition.
Does the d to the n count for n insertions or just one?
Oh, d to n is actually regarded as like n magnons.
It is n magnons.
Yeah.
It could just be n derivatives of z.
Yeah, but in field theory it's just like n derivatives. And the way to deal with these like different flavors or different species of magnon is to use this twister-like. It's convenient to use this oscillator representation or twister-like, ambitwister-like representation. So the basic fact, which was used also in other talks in this workshop, is that fields in n equals 4 super mils has an oscillator representation. And in particular, so this is precisely like y and z, which appeared in other talks, like Nathan's talks as well. So there are like some difference from the notation that I'm used to. So I'm not fully sure if I'm using a consistent notation. But the point here is that so you regard these as creation operators and regard these as an annihilation operator. Then you start constructing. So these are just like a 1D harmonic oscillator. So these are fermionic. These signs are fermionic, and these mu and lambda are bosonic oscillators. And using these oscillators, you can just represent all the fields or letters in n equals 4 super mils in terms of oscillator. For instance, the self-dual field strengths can be expressed in this way, whereas the fermion can be represented in this way. And the scalar field, which are in the antisymmetric of SU4, can be represented in this way. So this is also like a use, for instance, like in Fernando's ancient work about string. And
but just in terms of history, this goes back to BMN, does it, or is who does it go back to?
Gunidin, I think. Like this oscillator construction is like well before. I think already Gunidin was given like an oscillator construction.
This is Gunidin. Okay, I was attributed to Spicer.
For the algebra, I think.
I think that's right.
Yeah.
right, so I don't know if Matthias and Rajesh are talking about the change of the vacuum, but yes, that's indeed what I'm going to say. So this is one way of constructing, like probably like one most canonical way you find in the literature of constructing the states in terms of oscillators. But because these are fermionic oscillators, you can easily kind of change the vacuum by starting, instead of like considering, for example, this vacuum, you can start constructing states using, for example,
It's just one small point. The size, don't you break up the size into two component size?
Yeah, that's what I'm.
Oh, that's what you do. I see. So that size is a 4-component one, but you're just about to break it up into two.
Yeah. So if I start, yeah.
Mu dagger psi, mu dagger psi.
Right. So this is precisely what I was going to talk about. So in order to make connection with integrability, it's more natural to start with this kind of vacuum, and you can easily go back to the original vacuum by multiplying psi1 because of the anticommutator. But the point here is that now this corresponds to Z. So this is more natural for describing all the states in terms of the oscillator representation, or in terms of like a spin chain description, because I want to view Z as the vacuum and then describe other excitation as the magnon.
Mu dagger.
And if you start from
So is there any understanding of, so somehow you're stuck on n equals 4, d equals 4 superinnals, but originally you had two scalars. Is it something that integrability tells you that you need to do n equals 4, d equals 4? Do you have any understanding of why you are doing n equals 4, d equals 4?
okay.
So when we had,
I mean, could you do this for APJN?
Yeah, we can do it for APGM, but as well. But to answer this, to answer the Nathan's question, actually, so far I'm talking about one loop. Yeah, at one loop, actually, many other gauge series are also integrable.
Which ones? Can you tell me which ones?
For example, I think like a pure males also has some like an integrable sector.
But it's not completely integrable, is it?
Well, there is a subsector at one loop which is integrable.
But if we take all letters of pure Yang-mills,
all letters no. Yeah.
I'm just trying to understand how you know this. Is it just trial and error, and you say, well, this looks integrable, let's try it? Or
Yeah, well, so far it's just trial and error. So far, what people did was like just look at different gauge series and then see if the Hamiltonian that you get from the addition operator is integrable or not. It's really trial.
It's not a property of this. I mean, I would have guessed it is some property of the gauge theory that tells you if it's integrable or not.
Okay. So if you want to answer this question, yeah, probably you should ask Niklas, because in the past few years, Niklas has been trying to kind of formulate a Yankian symmetry at the level of the Lagrangian. And what he observed is that for that particular Lagrangian that's given by n equals 4 supermers, you can actually define the Yankian. But if you try to do the same in other gauge series, the Lagrangian is not Yankian invariant.
I guess that's an exclusion, but it doesn't answer my question. What is it about n equals 4, d equals 4 that makes it special?
Okay. Well,
is it something to do with supersymmetry? Do you need? I mean, suppose is there some three-dimensional analog of this, or?
Well, APGM is also integral.
But it's also supersymmetric.
That's also supersymmetric. But you can also break supersymmetry, for example, beta deformed n equals 4 supermers also.
So there's all these things known about two-dimensional.
I think it's basically the Niklas construction.
Two-dimensional integrable theories are there. I thought they were all somehow reducible from self-dual Yang-mills in four-dimensional.
Okay.
I'm just trying to understand what the current knowledge is. If it's still the same as it was 25 years ago, then people say no.
I think the one. Yeah, so I think like one interesting recent development is the one by Costello's holomorphic Chern-Simon theory. Like he found some very systematic way of constructing integrable field series, and indeed, like you can construct not this spin chain, but you can construct a AdS5 times S5 sigma model in that language. Okay, so yes, so now, so this oscillator representation is very nice for describing magnons, and if you start describing all the magnons starting from this new vacuum, which corresponds to Z, then you find that elementary magnum carries two indices, and each indices runs from 1, 2 or 1 hot to hot. So 1, 2 is bosonic indices, and 1 hot to hot fermionic indices. And so this is a little bit vague, but let me just write down explicit relation. So 1 dot corresponds to basically covariant derivative, and 1 dot. So this is just a spinorial representation of the covariant derivative. And then if you consider 1 hot dot, and that corresponds to x. And so these are like elementary magnons, and whereas now like f alpha beta or z bar are composite magnon, by which I mean like it consists of 2 or more magnons. And the precise relation between this magnon representation and this oscillator is that if you can so all these magnons are like a bilinear of curation operator acting on 0 bar. So they define elementary magnons, whereas to construct the composite magnons, you need more than 2 creation operators. So let's quickly see that's the case. For example, in F alpha beta, as you can see that in the original vacuum, you just needed to act 2 creation operators, but because we changed the vacuum, so you first need to destroy these psi 1 and psi 2, and then multiply these mu's. So that's why you need like a 4 creation operator from the point of view of a new vacuum, so that's why this is composite magnon. Okay, so this was just like a description of magnons, but the point here is that now beta and that gets modified, so the energy formula stays the same. Energy formula stays the same, but now so this becomes matrix because we have different kinds of magnons, and this S is a complicated object which is a matrix which depends on AA dot, BB dot, and CC dot, and BB dot, because each particle carries 2 indices. So this now the Bethe-Anders equation is a matrix valued equation, which basically says that E to IPL times the product of matrices is equal to 1.
So the momenta can't change just by kind of 2D kinematics?
Sorry, the momentum.
Like S only depends on 2 momenta.
Right. Yeah, S only depends on 2 momenta, and
it doesn't depend on incoming and outgoing momenta separately.
Okay, so that's a good point. So because of 2D kinematics, actually like a scattering is elastic. So if you have a particle with rapidity u, then it goes to rapidity u, and the particle with rapidity
So all the magnons have the same mass?
Yes, here all the magnons have the same mass.
So does this S matrix factorize in terms of the individual constituents?
You mean like A and A dot? Yes, yes, that's true. Right, so there is one point I didn't emphasize. So these A and A dot are basically like a fundamental or anti-fundamental representation of what's called PSU 2/2, which is basically the stabilizer group of this vacuum. And because we have like so both A and A dot are separately like a representation of PSU 2/2, actually the full symmetry group of this scattering S matrix is PSU 2/2 squared, and because of the symmetry, matrix structure actually factorizes into 2. Okay. So right, so this was the story for one loop, but
So why did you say PSU2/2 and not PSU2,2/4?
right, so the reason is the full symmetry of n equals 4 supermus is PSU2/4, but here all these magnons, in order to go to magnon representation, I first fix the vacuum which are made out of Z, and this PSU2/2 is essentially stabilize a group of this like a vacuum.
Like a little group?
Yes, exactly. Yeah, from AdS point of view, like it has a interpretation as a little group of a particle, like a static particle in AdS. Okay, so and let me just say that people also succeeded in uplifting this Bethe-Anders equation to finite to Hooft coupling. And if you go to finite to Hooft coupling, then the relation between this U and momenta also change. And of course, the S matrix change as well. And let me just briefly write the formula because some of the formula becomes a little bit important. So this, instead of U plus I over 2 over U minus I over 2, we now have this expression where x plus minus is defined as x U plus minus I over 2. And function x is a non-trivial function of U, which is defined by solving this equation. This is called a Joukowsky map. And G is square root of lambda over 4 pi. And so there is an analogous expression for S matrix, but it's super complicated, so I'm not going to write it down. But important point here is that x of U, so if I solve it explicitly, has a branch cut. And that means that because E of IP is given in terms of ratio of XU of U.
Sorry, Shota. So I guess so here we went from one loop to any number of loops.
Yes.
And well, this is just amazing, of course. And in principle, we could have put any function of lambda there, and this structure would be the same.
Right. Yeah. So this G, the relation between G and lambda is actually not. You cannot really.
Right. Right. So I guess you do perturbative computations and you check that it's just that. Very nice.
But V is a function of what? And then it's square root of lambda over 4? I mean,
It's just that.
G is a number.
G is a number.
G is a square root.
G is equal to.
It's not a function.
Yeah. G is a square root of lambda over 4 pi.
But you could have put any function of lambda.
Yeah.
Been integrable too, but.
Yes, but okay. Yes.
But there's only, I mean, G is the only pure number that enters in this whole game, right?
Yes. Because we are in the larger limit, so coupling is the only number.
So as lambda goes to 0, we get the first formula that you wrote down.
Yeah. If you send lambda to 0, which is G to 0, then x become proportional to U. And then this relation becomes U plus I over 2 over U minus I over 2. And what I just wanted to say is that because E to IP is written in terms of ratio of x plus U, x minus U, so this E to IP as a function of U has two branch cuts. and one corresponding to branch cut of x plus, and the other corresponding to branch cut of x minus. And what happens if you go through the branch cut and comes back to the second sheet is if you go.
Sorry, Shota. So this is the behavior of x in the u-plane.
This is behavior of e to ip.
Oh,
That's over x minus.
Because like each x has one branch cut. And what I just wanted to say is that if you go this monotony, or like going through the branch cut and comes back, then x plus of u becomes 1 over x plus of u. So if you go through two branch cut, both of branch cut, it's probably a bit unclear why I'm talking about this, but I hope it's going to be clear soon. Then both of x plus and x minus becomes 1 over x plus and 1 over x minus.
The lower dotted thing is solid, right?
Right. Sorry, so but it's a different branch cut.
No, the lower one.
So they differ by I.
Oh,
And
you're not back on the
different
same sheet.
Yeah, you are not going to end up on the same sheet because like you have like 4 different sheets basically.
Oh, I see.
Oh, sorry, but those, okay. But those branch cuts, surely they differ by an imaginary shift by I, don't they? I thought I got that wrong.
Yeah, well, sorry. So yeah, these 2 branch cuts are separated by I.
Yeah. So this is where you start to see ladders forming.
Yes. And what I wanted to say is that because of this, so if you do this, then e to ip, which was originally x plus over x minus, becomes e to minus ip u.
So I missed the discussion. So the first is what happens if you cross the second branch cut,
Yes.
and then if you cross the first branch cut,
And then second branch cut.
and then the second branch cut, that is what happens.
Yeah.
Okay.
So essentially, like, this is a branch cut for just for x plus, and this is just for a branch cut just for x minus. And if you cross like each of branch cut, like the corresponding x variable like flips. So and I said like if you do this move, analytic continuation, e to ip becomes e to minus ip. And from the point of view of 2D theory, this it's probably not very obvious, but this is interpreted as a crossing transformation, which basically changes particle to antiparticle. Here I was only talking about momentum, so it's probably not very clear that it really corresponds to crossing transformation.
But if you only cross one branch cut, the interpretation is not so clear?
The interpretation, yes, okay. Right. So, yes, there is also physical interpretation of crossing only one branch cut. So, in order to explain it, let's draw this 2-dimensional space-time on which this spin chain or like a string Worley theory lives. And what I said is that if you cross both branch cut, then if you start from a particle, then you basically move to like a particle living on the out state. So this is like a crossing transformation. But if you just cross one branch cut, then we also know what the physical interpretation is. The physical interpretation is that you move particles living in the in state here, like to here, which means the particle living in a space-time in which space and time is swapped.
And is that what people call a mirror or something? Or?
Yeah, that is often called mirror particle.
So is it the CPT conjugate?
Okay, so yeah, if you do this, then it's CPT conjugate. So there is an analog of CPT you can define on this like a 2-dimensional theory. Well, this 2-dimensional theory is a little bit weird because it's not relativistically invariant, but you can still define the analog of CPT, and this analytic continuation moves like basically does the CPT conjugation. Essentially, in the relativistic 2D theory, we have like a nice representation of energy and momentum in terms of what's called affinity parameter. And then if you do this analytic continuation, which is just shifting pi I, then that corresponds to like a CPT conjugate and particle-antiparticle. But here, this pi analog of this pi I is going through the branch cut.
So our original theory didn't have all of this because it didn't have an antiparticle to the y.
Right. So because it was like a just magnon, which is non-relativistic particle, and that's why in the one loop we didn't see it. And you can also understand it from this picture because in the weak coupling, this G, basically you set it to 0. So there is no way to cross the branch.
Are you going to say anything about how this was obtained, or?
Yes, okay, let me say that. Yeah, because this is actually something nice about this integrability story, because people obtained this by combining intuition or putting together intuitions or the results people obtained from gauge theory and also string worksheet. So let me just say a few words.
Right, and this is the formula that is only correct at large L, right?
Yes.
So this includes the dressing factor?
This does not include Virasoro.
The dressing
The
factor.
dressing.
For loop part, this isn't something.
Okay, so this S, I implicitly assume that includes dressing phase. Okay.
Sorry, so this includes everything.
Yeah, this includes everything.
But you haven't told us what the new S of lambda is.
No, it includes everything, but it's still only correct at large N.
Not the wrapping factor.
Large N and large L.
Yes.
The wrapping is not there.
Okay, so.
L loops.
Alright, so let me just say a few words about how people determine, in particular, this and then this. Well, let me just focus on this, like S matrix, because like as a byproduct, you also determine this the formula for this guy. Sorry, it's on depends on already. So what people imposed is the first thing people imposed is the SU2/2 symmetry, because as I said, each magnons are representations of PSU2/2 square. So this S matrix must commute with the generator of PSU2/2 square. So this is, of course, like the first thing people you would impose if you consider S matrix of a series with some symmetry. But as you can imagine, this is not very strong, because this is just a global symmetry constraint. And what really changed the game was to impose the invariance under the additional generators, which from the point of view of PSU2/2 square, they are basically central charges. So what are those central charges? So the interpretation of the central charge, to explain what the central charges are, from the gauge theory, we just need to remember the basic transformation rule, especially how supersymmetry act on the fields of n equals 4 supermills. So, as we know, that supersymmetry converts boson to fermion, but in n equals 4 supermills, if you act some supersymmetry to fermion, then it gives some boson, but it also gives this. So if you choose appropriate supersymmetry, then it also gives this kind of term, which is kind of like an analog of covariant derivative. First of all, I must say that Q acting on fermion typically gives rise to like a boson acted by the covariant derivative. But because of n equals 4 supersymmetry, you also get this kind of term.
Where Z is what?
Z is the complex scalar field I was talking about. And this part, as you can see, has a structure of the gauge transformation, but it is a field-dependent gauge transformation. And in particular, if you just analyze some anticommutator of some particular Q and Q prime, then you can see that this basically gives rise to, well, this anticommutes up to this field-dependent gauge transformation. So there is some particular choice of Q and Q prime which anticommutes to this guy. And this is basically what I meant by P. And the first thing to notice is that, so this generator, which is just a field-dependent gauge transformation, comes with GM-MILS just because it's a gauge transformation. So it kind of knows about the coupling constant dependence. So this was the reason basically why we could fix the coupling constant dependence by imposing the invariance under these high central charges. But another good thing is that this field-dependent gauge transformation, P, has also nice 2D interpretation. So let me just say what that is. So let's consider the action of this P on kind of state, the spin change state, which consists of a bunch of Z. With yes.
The Q and Q prime, are they supersymmetries that leave Z invariant or transform Z?
Q and Q prime leaves Z invariant.
Okay. So should they be then part of the stabilizer group of the vacuum? Shouldn't they be part of this?
Yes, yes. So that's why, so this is obvious stabilizer group of the vacuum.
There's more.
Then there are actually more if you start talking about.
So they appear as central charges if you try to write down the algebra for this PSU2 plus 2.
So what I wanted to say is that this P also has a nice spin chain or 2D interpretation. So let's consider this kind of state, which is a string of Z, but one Y at nth position. And then see how this P acts. And I also assume that this chain is infinitely long. So then, this is a commutator, so I can just break it up into two pieces. And the first piece basically adds one Z in front of Y. So then, I get something like this. Now the position of Y is shifted by n plus 1. But then, the second piece, the position of Y is not shifted. And clearly, this is the discrete translation of spin chain. And this is basically the reason why imposing this symmetry also fixes this kind of dispersion relation of magnons, because it knows about a translation of the 2D theory. So let me just summarize. So on the one hand, this P knows about the coupling constant dependence, and on the other hand, this knows about the 2D kinematics. So that's why it was very constraining to impose the invariance of P and K, and that's why people could determine basically the S matrix and this P of lambda.
So it doesn't act the same way on every letter?
Yes.
So I would have thought then that all it does is to say that the whole thing is invariant under overall translations.
Yes.
That doesn't sound very constraining.
Okay. So one thing I should say is that if you really act this P onto the single trace operator, then the action is of course 0 because it's
because cyclicity. Yes.
Because of the cyclicity.
Right.
The reason why this action of P was non-trivial is because we are considering a very long chain.
So you open
open them up and then scattering magnon on top of the chain.
Right. But it sounds like it would, even in that very long chain, it sounds like it would just impose momentum conservation of scattering on that long chain, right? Oh, but you're saying it's because it's this discrete momentum, that's why it's constraining?
Okay, so what actually this P imposes is this one. Sum over e to ip of individual magnon, the product of individual magnon is 1. So it's a little bit different from momentum conservation. It's more like a total momentum adds up to 0. Well,
Yeah, I think you don't impose cyclicity until the end, right? That's
yeah.
If you impose cyclicity on just then it would be completely trivial. But you impose that somehow at the end.
Yeah, you're moving it relative to the others, I guess.
Right, yeah, indeed. Like we are moving them relative to the other.
But I thought you were moving them all. Right? All the z's stay fixed. And you're moving. Oh, maybe. I thought if you had this infinite chain, there's a bunch of z's, and then you're just moving everything one step forward.
Well, that's the product. That's the product that he wrote. Is when you move everything.
Yes.
But each p is moving one.
Good. Good.
Right, so it's like a local version.
Yeah, they keep their U's.
Yeah, it is that is like momentum conservation, but on a line,
On a line.
not on a circle. Yeah.
Fine. But it sounds like you're saying the momentum is 0, right? Because it's the condition that the product, sum of momenta are 0 up to 2 pi.
That's the cyclicity of the truth.
Yeah.
That's the cyclicity of it. But if we were just on the line, we wouldn't get that relation, right? You could have any momentum you want.
Yeah. You can get any momentum you want.
Okay, and then finally you put cyclicity.
Right. Yeah. Okay.
I somehow don't see. I mean, later.
Okay. I understand your point. If you just, I'm not saying just
We have K2, right? Maybe K is stronger.
the just imposing P fixes everything, but of course, like we need to remember that P is an anticommutator of Q, so it's kind of like related to the supersymmetry as well, and that kind of sounds like a complicated, like a subtle structure, basically determines things.
I see. The fact that you know you had an independent action of the supersymmetry and you know it must square to something simple is constraining. Okay, thank you.
So the p lambda of u you wrote there is the eigenvalue of the p opposite p.
Yes, basically that's,
Can you convincing perturbatively in lambda, but are you sure it's also true non-perturbatively in lambda?
Okay, so here yes, indeed, like this field transformation that I wrote down is just the classical field transformation, so it's more like a perturbative intuition. But on the other hand, I don't have the time to say that, but you can also derive this centrally extended PSU2/2 squared from the string Walsh theory by gauge fixing.
What Walsh string theory is starting?
Okay, so you start with the meta-extended reaction,
Yeah.
and then choose what people call generalized light-cone gauge. So
You can tell me.
okay, yes.
Inputs for supersymmetry is very constraining.
Yeah.
It's hard. It would be hard to change the right hand side there, right? Consistent with everything.
that's true.
I don't think it would be easy to do.
Yeah. You could put a different function, maybe of G and Mills, but that's it.
This formula has been proven, has been checked to at large lambda?
Yeah.
And K, are you going to say anything or?
K is, K, I'm not going to say anything, but K is something that shows up in the anticommutator of superconformal.
Does it have some nice?
Yes, so it's actually, so this one, it's hard to deduce from the transformation of the classical Lagrangian classical fields, but it's required to be there because of the closure of the algebra in a consistent.
Sure.
But do we know how it acts on like a chain?
Yeah, that's the inverse.
But we want to write some. I see. So you have to
In the opposite direction. You remove z like that.
Okay.
I see. So it's just you're saying
It looks like P minus 1 or something like that.
Yeah.
So should I regard these formulas essentially as the definition of G angles?
Yes.
Yeah.
Yes.
Sorry, one thing I didn't realize is the top one will increase the spin chain length by 1, right?
Yes.
Oh, so then it's more non-trivial. Okay, now okay, and the bottom one reduces it by 1.
Yes.
So it's not just a translation.
Yeah, it's not just the translation.
Okay, thank you.
on the infinite line.
Yeah. So these are these spin length changing operators. Right.
Okay, so this is the finite coupling Vedantats, and let me just say that by solving this equation, we can compute the energy or anomalous dimension or conformal dimension of the operator at large L, and actually the result that you get is valid. Will include all the perturbative 1 over L corrections. So again, let me just remind you that L is the length of the operator. But then, in addition, there are like e to minus ml correction coming from some virtual particles interacting with the physical magnons that we have for the states. And these can be systematically included by what's called Lustre formula. And one can also resum it into TBA, what's called thermodynamic Vedantats or quantum spectral curves. But I'm not going to talk about it because I want to move on to the correlation functions.
Sorry, one general question. These spin chains act on the set of states that had equal classical dimension, right? They don't mix between states that had unequal classical dimension. Is this right? Now, in perturbation theory, it's clear that that's how it should work, because dimensional regularization, you can only get log mu. Yes. And so you can't mix, just dimensionally you can't mix. But was it clear that non-perturbatively this feature would persist?
I think non-perturbatively, I think it's not true.
Not true, I see.
Yeah, there are several examples. For example, there is one nice example. So you consider some like an operator dimension inserted on the Wilson line, and supersymmetric Wilson line. And there is the Susy-Wilson line coupled to one scalar, which is phi 6. And then there is operator corresponding to inserting extra phi 6 here. But this operator is known to, if you go to the strong coupling, at some point it starts mixing with like a phi 1, phi 1, phi 2, phi 2. So this combination. And obviously, like at weak coupling, these have a completely different dimension. This is 1 and this is 2. But it's known that this continuously goes over to something like this if you go to strong coupling.
And I guess it happens too for just single trace operators, right?
Yeah, this is also true. Yeah.
So here we may have level crossing,
Yeah.
which we don't.
Which we don't say. Sorry, so this Bethe ansatz was completely on the space of classically same dimension operators, right?
Right.
At what stage do we see this, that these start talking to each other? In this spectral curve or wherever do we see that?
Yeah, I think it's at the level of this like a e to minus ml correction, which can be captured by quantum spectral curve or TBA.
Large L, you mean, okay, so most of them is large R charge, that's what you mean by large L, right?
Yes.
So can you use BMN to get these, to compare this with at large, at large?
Yeah, that's what people did. Yeah, BMN. Yeah, you can.
So we don't need the Massage siphon, do we?
Sorry, we don't.
Do we need that to check this? I'm asking about large lambda. Can we use BMN to check that it's valid at large lambda?
Yeah, certainly. Yes.
Sorry, the Susy-Wilson loop. That was what was the connection of that?
Okay, so this was just a side comment about the possible mixing between operators whose classical dimensions are completely different, because this is one and this is two. But yeah, this is
And what do we know about small or finite L?
Small and finite L, we can solve it using TBA and quantum spectral curve.
Exactly for any L? Is that
Numerically for any L.
Sorry?
Numerically for any L.
So let's say L is equal to 2, right? The Konishi that you can construct for all lambda.
Yeah.
But do we know the non-perturbative for that it's not,
Well, you can make a plot, and then that smoothly interpolates the weak coupling answer and the strong coupling answer.
but we don't know the strong coupling answer for small.
For Konishi, because it's a short string, the leading strong coupling is given by a flat space spectrum.
Okay, maybe you can tell me that argument. I don't know. I don't know how to compute Konishi from flat space.
It's just the mass of that corresponding string space in flat space, and then put an alias.
It's 2 lambda to the 1/4. It's 2 lambda to the 1/4.
I know the answer, but I don't know how to get it from flat space. I don't know how anybody got it from flat space.
Okay. Yeah.
You can tell me later.
Sorry, how did you understand the mixing from the Wilson loop? Though? So the Wilson loop is just some supersymmetric.
Yeah. So this is not about Wilson loop. This is an operator insertion on the Wilson loop.
Right.
So these are like a defect conformal defect CFT operator, and then I was just mentioning in answering Shiraz's question that there are examples in which people studied in detail how these two operators mix. You turn on the coupling.
Ah, okay. So
Before you go ahead, so can I ask 2 very general questions? So first, if you compute this in perturbation theory, you have some small lambda expansion, and the small lambda expansion has a finite radius of convergence, and I am very happy with that. If you take something like Konishi, you compute it somehow, you get 1/λ expansion. That is asymptotic, right?
Yes, that's it. Yeah.
And does it have also non-perturbative corrections, like e to the minus lambda?
I think that's a good question. For Konishi, I don't think people understood that.
I see.
Because so far, we can only approach strong coupling using numerics.
I see. So you only, I see.
Yeah. So let's now briefly mention about correlation functions. But before starting to talk about the correlation functions, I didn't emphasize much, but this, for example, central extension of PSU2/2 square and also some of the structure that I discussed so far can also be like derived in part from the string worldsheet theory. And the idea is to take some kind of, there is an analog of light congauge in AdS5 times S5 string theory, which is called generalized light congauge. In which the Hamiltonian of the after gauge fixing becomes delta minus J. J is one of the R charge, whereas the length of the string becomes proportional to J. So this is the analog of the light congauge in flat space, in which the Hamiltonian becomes P plus. I never know which one is P plus, but and the length of the string becomes proportional to P minus. So there is such a gauge in which you can try to do perturbative analysis, and then from that analysis you can conclude there is also a PSU2/2 square centrally extended symmetry on the gauge fixed Lagrangian worldsheet theory.
And do you see some hint of this oscillator emerge on the worldsheet?
Yeah, that's more or less obvious because that's the magnons that I described just corresponds to A+8 bosonic and fermionic oscillators on the gauge fixed Lagrangian.
Is this BMN limit or this is?
This is basically like expanding the string worldsheet around the BMN and then gauge fixing, so that you kill the unnecessary degrees of freedom.
Sorry, when you said 8+8, so it's SU4/4 or it's?
Okay, so I had like MA a dot.
Oh, it is. Sorry. Okay.
This is a magnon, and we have like 8 bosonic and 8 fermionic excitation, and because like this runs from 1,2/1.
Oh yeah.
So sorry, are you saying that if you just work around this BMN point and expand, you basically can derive the Lagrangian that Rajesh and Matthias were working with?
Well, that's not true. Sorry, the BM. You mean like weak coupling?
No, not weak coupling. But I was just thinking the variables.
Mm-hmm.
You get some Lagrangian in these oscillator type variables, and is the Lagrangian more or less the same form?
Oh, you mean like a starting? Okay, so that's different because
Oscillator variable.
yeah, the oscillator variables are same, but the Lagrangians are different because we are starting from like a AdS5 times S5 string worldsheet.
you're starting from BMN. I mean, I don't think it's fair to say you're starting from a covariant Wiltshire. You're starting from BMN, which is already PSU 112, only PSU 112 squared invariant. So the difference with what Rajesh and Matthias is, they're starting with a description which has the full symmetry manifest. This is already...
But is it a version of that? I mean, is it sort of the same kind of Lagrangian?
It's like a light cone version of... So in the large R-charge limit, then it's kind of like a light cone version of what they're doing.
Yeah.
So there must be then maybe a version of the full covariant Lagrangian, which you can kind of gauge fix to get that.
That's the idea. So, but okay, so what you...
like in maybe the thing that we were trying similar
I mean, the difficulty is, at large R charge, it's not difficult. The difficulty is at finite R charge. That nobody knows how to do.
Right. But even at large R charge, you could still try to work in that sector. And
Large R charge is just a plane, so you take the plane wave limit of what you do, and then you, well, not what you guys do. I mean, you have zero tension, but if you had, you can do it at finite radius. You don't have to do it at zero radius.
Can you guys put your Lagrangian in this light cone gauge?
yeah, that's what we
It's zero tension, it's the opposite.
Okay,
No, but
technically.
you can look at the large length,
large W or the large
limit. That's basically what it is, right? W is the length of the
chain, and so yeah, this is what we are trying. We are trying to recover the BMN limit from our world sheet.
We're using the same light cone gauge. This J is...
Yeah.
well, looking at large W.
Yeah.
You're saying you don't need any tension for that to work? I mean, don't you need something
I
that...
don't think you need any tension.
Do you need something that keeps the string from just exploring everything?
So why couldn't you do BMN at zero tension? Can you?
Yeah, you can. The BMN formula, when you extrapolate to zero tension, you get
you just get trivial.
free Yang answers.
Oh, I see.
Oh, I see.
And then, like,
It's not massive.
yeah, energy is just 1 or something, right?
Yeah. The energy
But
is
I mean,
just
it links up with the variables that appear in our description.
Oh, okay, I see.
Just a trivial answer.
Okay. Yeah.
You take L to infinity and then you can...
Yeah, indeed. Okay, so let me just say a bit about
You should go ahead and...
correlation functions. So far the story was about how to compute a spectrum, which basically governs the 2-point function, but we also want to understand the correlation function, especially, for instance, 3-point function. So let me just remind you how you compute the 3-point function of single trace operator in n equals 4 super mLs in the planar limit. So that's just like doing a bunch of weak contractions. And one thing I already wanted to note is that, so here, number of weak contraction between operator 1, 2, let's call it L12, and also call it L23 and L21. These numbers of weak contractions are completely determined by the lengths of the operators, because obviously these numbers need to satisfy this equation. And we have 3 variables and we have 3 equations, so everything is fixed. And we want to view this as the analog of the statement that there is no integration, so, well, basically no integration over the moduli space over world sheet moduli space if we consider 3-point function of the vertex operators. So, and just to say that this connection, this relation is more general than this trivial case, let me just also draw one for the 4-point function. Again, just a trivial exercise. So I have like the typical connected weak contraction of the 4-point function. It's something like this, and then you just start contracting the operators. And you see that there are like 1, 2, 3, 4, 5, 6 edges, and 6 edges, but minus 4 equations coming from like a length of the operator. That leaves 2 degrees of freedom. So we need to kind of like, even when you are doing the like just tree-level reconstruction, we need to sum over like a 2 real degrees of freedom. And we want to interpret it as basically the moduli space, the dimension of the moduli space of the 4-punctured sphere, which is again 2 real dimensions.
Okay, this is, okay. It's just words, but
yes. Right, so what I'm going to present is integrability approach to compute correlation function, which is just like a bunch of rules, and we still don't understand how it really comes about from the worksheet, but there are some hints that might be suggested that might be related to the worksheet picture, and that's what I wanted to present.
In the case of the symmetric orbifold, there is a very precise realization of this picture. It's not just words.
right, no. There is really as a sum, right? That's
the sum, but that's the whole point, that the sum is of the same dimension and there's a limit in which it becomes an integral. When you have large operators, then the number of contractions, the undetermined variables is effectively like a continuum. Because if I take all the L1, L2, L3, L4 to be very large, then I effectively get a continuum. And that's exactly what the string worldsheet dual theory gives you. So you get the discrete points, then you have
So once you put in the radius, then of course, or the interactions, then of course you go.
Then of course I think it will you will always be in the continuum, so to say.
Right.
But
they're just doing the free case, so that the
yeah.
free case,
But in the free case also you see this realized, because the symmetric product orbifold is
you get some, but not a. They want to get. Okay, I don't know.
Yeah, the sum becomes an integral in the when the size of the operators becomes very large.
I mean, in the symmetric orbifold, you have to sum over all the covering maps, and you can enumerate them, and then the limit where all the twists get large, this approximates the integral over the full world.
So in the limit when L goes to infinity, somehow the sum becomes
The sum becomes an integral.
Yeah, because the covering maps become dense, and you can...
And even when L is finite, it's a sum even on the string theory side, because you get this localization. So it's a sum is equal to a sum, and the integral is equal to an integral.
No, finish.
No, just so the arrow is really only in the L goes to infinity limit. That's the claim.
Well, yeah, you get the continuous moduli space in that limit, but
For finite L, it's a finite sum, so it can't be the integral over m over 0.
Okay.
Yeah, well, I didn't write equality, by the way. So.
I understand there's something to do, but I just don't know how much.
So if I try to do it for 5, and if I'm doing the math right in my head, which I might not, you have 10 minus 5, which is 5 real, 5 variables to sum over, which doesn't seem to correspond to
No, it's not 5. The number of Wick contractions.
10.
It's not.
Isn't it 5 choose 2?
No, it's planar diagram.
It's planar, so
Oh,
yeah.
I see.
So you get 9 actually.
Oh, I see.
9.
Thank God.
So, yes, so Rajesh mentioned that, okay, so in the, if you use like what Rajesh and Matthias are doing, then there one can map this like a summation over like a L's, the discrete sum, into the moduli space, and then there is a concrete mapping between this within the Feynman diagrams to the covering space, in the twist the covering space. Basically, what integrability, in particular what's called hexagon approach, does is to kind of dress this tree-level picture by magnons, and then promote the result to finite coupling. So basically, integrability tells you how to kind of promote this tree-level picture into the finite coupling. And actually, in the hexagon approach, this sum is always a sum. So this is a little bit confusing point, and especially probably it's different from what Matthias and Rajesh are thinking about. I guess in your picture, probably like it's more natural to have a continuous moduli emerging once you turn on the coupler. But here, at least in this integrability approach, what we get is always a sum.
Is it the same sum?
It's the same sum. It's exactly the same sum, and the integrability just tells you how to decorate what's inside. So this is one weird point, and it's probably related to some kind of gauge fixing we are implicitly doing.
It sounds like, for me, it's naive, it looks like perturbative Feynman diagrams. I mean, of course you have a sum of Feynman diagrams.
Right.
Okay.
Yes. Yeah, but integrability is basically gives you a way to convert each.
Sure. Yeah. You know, of course, getting finite lambda is difficult with Feynman diagrams.
Yeah.
It sounds like.
So let me just draw a picture for 3-point function. What I mean by address 3-point function. So from now on, I'm not going to draw equality. I'm always like using this. So you need to interpret what I really mean by this. But so as I wrote there, 3-point function at tree level is given by this diagram. On the other hand, on the string theory side, the 3-point function is given by a pair of paths. And basic idea, and then, okay, so this comes with L12, and this comes with L23, and this comes with L31. So the basic idea of the hexagon approach is to cut this string worldsheet into 2 parts. Then you get the 2 hexagon, like one here and one back. And then the basic idea is to cut this worldsheet into 2 halves and then glue them back together by inserting a complete basis here. And the complete basis on this worldsheet, especially in the integrability approach, is given in terms of like a magnum excited states. So if I were to draw what I really mean by this, the leading term comes from basically choosing vacuum for all these dashed edges in which we don't have any particles. And the next leading term is given by inserting one magnum in one of the edges. So let's choose this edge, which connects 1 and 3. And when you connect them, we also introduce this phase factor, this propagation factor. So here I have a magnum with momentum u and magnum with momentum u. So the basic, let me just say a few words about this factor. So this factor looks a bit mysterious, and of course we don't know how to really derive it, but the interpretation is that in order to go from this hexagon, or this hexagon, to the next hexagon, which is the back, you need to cross L31 propagators, which define some kind of like a length, propagation length. And that's why this magnum needs to come with a factor of E2 minus E, energy times L31.
So this is a prescription that produces the correct answer, or
this is a
sort of string-inspired prescription to produce the correct answer, or is it derived from first principles in some sort of more...
Yeah, it's a string theory inspired prescription that reproduces the correct answer.
And, you know, if we try to apply this to some other theory, let's say pure Yang-Mills, do you expect a similar prescription to hold?
Yes, we actually expect something similar to work, but in order to really convert this into a computational framework, we need to know what this is, which we call hexagon form factor. So this formula basically converts the 3-point function into a sum of product of these hexagons. But in order to really compute something, we need to know how to compute each hexagon. And for general large N theory, I think it's probably hard to systematically find a way to compute hexagons, but we expect something similar to work in general large N theory. So now, as I said, once you assume this structure, everything boils down to computing.
So just to clarify, so you expect the structure to be generally true, but that the ability to compute the elements comes from integrability.
Yeah, exactly. So we need to understand, yes. Basically, this is what we call hexagon form factor.
So it's enough to know all the magnons along one leg, or?
Sorry?
It's enough to know the hexagon with all the magnons along one leg, or you also get mixed terms?
It's enough to know. It's enough to know this one, and the reason is because of again this crossing and mirror transformation I explained it before. So again, each magnon comes with their own a branch cut. And if you start crossing the branch cut, here you start moving the particles. So this is just a part of the rule. So what I'm presenting is just a bunch of rules. I don't know how to derive it, but it works. So now to really compute this object, which we call hexagon form factor, we basically determine them by solving a set of bootstrap axioms.
So that's why you call it a hexagon and not a triangle, because you can move this.
Yes, indeed, yeah. So there are several axioms, but the first one is what's called Watson equation, which means that if you have two particles and swap the order, then these two are related by the S matrix.
So the quotation mark in the bootstrap axioms means that you can't really derive it, but it's motivated by a natural...
Right. So again, this is a little bit different from conformal bootstrap, because in the conformal bootstrap, most of the axioms you can, at least those are very solid, and at least one can hope to derive it, even if it's not mathematically rigorously derived. And another axioms which is important is that, so let me just first write the equation and then explain. If you take the hexagon and then do some analytic continuation, which basically, so this 6 gamma analytic continuation is basically going through this analytic continuation 3 times. And if you do it once, we expect particle to move here, and then if you do it twice, particle moves here, and then if you do it 3 times, the particle moves here. So this is really this is one very important characteristic of a hexagon, and that's why we call it hexagon. And this is another axiom. And so there are a couple of more axioms, but I guess these two are most important, and I'm not going to write other ones. And by solving these, by imposing these axioms and trying to find the answer, you can actually determine the hexagon form factor and at finite coupling. And the coupling dependence basically comes about because of this, because this S matrix is defined at finite coupling, so you solve it, and then you can define it.
Now, certainly it's small coupling you can compare with perturbative super Yang-Mills, but A large coupling, now there's nothing to compare with, right?
Sorry, the small coupling?
Small coupling, you say you get the right answer. When you say the right answer, you mean it's small coupling.
Yeah, it's small coupling, yeah.
A large coupling, is there any evidence that this is the right answer?
Yes, that's a good. Yeah, thanks for asking that question. There are some evidences. So before, talking about evidence, let me just say one thing, which is relation to the computation of entanglement entropy. Or more precisely, Renyi entropy in 2D integrable system, integral field theory. So this was analyzed by Hardy and Calabrese around 2005 or 2008. So as you probably hear more, or maybe not, in the afternoon, if you want to compute, say, like what's called Renyi entropy, which is defined basically as a trace of rho to n, where rho is so let's call subregion A and then complement A bar, a trace of A, the ground state. This is a partial trace. So you first prepare the ground state of some quantum field theory and divide the region into two, in the spatial region into two, and then take a partial trace over the region A, and that defines the density matrix. And then, you also need to normalize, but then you take like a rho to n, and that defines what's called nth Renyi entropy. So geometrically, so there is a nice geometrical way of interpreting interpreting the computation of the Renyi entropy. So let's discuss it for n equals 2. So for n equals 2, so this trace or partial, like a rho of rho squared, you can alternatively compute it by considering the two-sheeted surface and then computing the partition function on that surface. So where this edge and this edge is identified, and this edge and this edge are identified. So basically you open up, you cut the surface a little bit, and then glue them to the second sheet. So this is the definition of trace of rho squared in the Renyi entropy. And you can also view this, if you view it from this direction, what you have here is some branch cut. So this object, one way to compute this object is to regard this as a two-point function of like a branch point twist operator, what's called branch point twist operator, which basically creates a branch cut in this space. And in CFT, you can basically compute them by computing the conformal dimension of this branch point twist operator. And if it's a massive integrable models, then you can also try to compute it by computing some form factor by inserting resolution of identity. So this defines what Hardy and Calabrese called a branch point form factor. And geometrically, this branch point form factor for n equals 2 is very simple. So let's just, in the branch point form factor, you have some branch cut and then some in state. And then like this branch cut continues to the second sheet. But if you, for example, try to see how these edges are connected. Then it goes here, and then emerge here, and it comes back here and here and here and here, and then continues here. So you can alternatively draw this as an octagon, where there is some conical excess (2π). So this is basically the object Hardin and Calabrese computed in the analysis of Renyi entropy to the integrable field theory. And as you can see, if you go to this picture, then this picture is very similar to what I drew here. And the only difference is that in the case of hexagon, we have a conical excess pi, whereas in the case of Renyi 2, we have a conical excess 2π, and instead of hexagon, we have octagons. But the thing I wanted to mention is that a bunch of those axioms that I wrote down here are motivated what they imposed in this context. But it's not really derived, precisely because what we are doing is slightly different. It's like more like a half, like a 3/2 Renyi entropy. Okay, so
yes. Is it a 3/2 Renyi entropy?
Sorry, I'm not sure.
What do you mean?
it's.
I mean that's defined. So
yeah.
Is that what this is, or?
Yeah, I think it's probably 3/2. Yeah, I think it's 3/2 Renyi entropy.
But what? I mean, there was an S matrix that was like.
Oh, right. So also in Calabrese analysis, actually, they imposed a similar condition.
So they're working with it. They're assuming an integrable field,
right? Like a sine Gordon theory or Sinch Gordon theory.
I see.
So I'm not talking about the paper about CFT.
No, I understand. Yeah. But I mean, already, I think having a formula for a fractional Renyi entropy, like an honest formula that doesn't involve some analytic continuation, is pretty interesting.
Oh, I see.
I don't think we have that in any field theories.
I see. Yeah, thanks for the comment. Indeed. So this is probably some kind of like a analytically continued version of Renyi. Okay, so now I come back to Nathan's question, whether there is something that we checked on the string theory side. So on the string theory side, in this lambda going to infinity, we expect the 3-point function to be given by this kind of 3-legged surfaces. Essentially, like an area of the 3-legged surfaces is given by, is going to give you log of 3-point function. And then computing this area is a little bit complicated problem because it's difficult to explicitly construct a surface, but nevertheless, using the classical integrability, you can directly compute this area, at least in certain setups. And this is a kind of generalization of Audai-Maudesena story, which was done by Fernando. The main difference is that here, well, let me just say that the problem basically reduces to solving some kind of Hitchin system with 3 regular functions. And this problem, you can solve it, and then you can compute this log of 3-point function. And the final answer...
Even for long operators? So they're regular punctures even when it's some big...
Yeah, even for long operators, yes. So for long operators, the precise boundary conditions that you need to impose is not the one people impose in the context of Hitchin system, but you can still do it. And then you can get the expression for the area, and that you can reproduce it by resumming hexagons at strong coupling. And another thing I wanted to mention.
Why is it simple to resum hexagons at strong coupling?
That's because some formulas simplify, some of the integrands simplify in the lambda going to infinity limit if you just send lambda to infinity.
I think so.
But
You're
that's
saying
kind of infinite sum of.
Yeah, so, okay, so what happens is that the hexagon is going to be like infinite, complicated infinite sums, but if you send lambda to infinity, you see things start getting exponentiated. And then you can try to directly compute the exponent, and that is going to be matched with against the area. Okay, so what was I saying? Yes, and another thing I wanted to say is that, like I said, that constructing the surface is hard in general, but if you really take the limit in which L over square root of lambda going to infinity, so this is like a really, really long operator, then you can approximately see the structure of the surface, and then you see that if you read off the induced metric on the worksheet, there is a conical excess pi at one point, and there is another point at the back. You have also conical excess pi. So this also gives an evidence that this hexagon form factor picture is natural from string theory. So let me just end here, but ending with some comments and questions. So one thing which hexagon suggests is that at least there is a way to compute this 3-point function or 4-point function using this approach, in which like a moduli integration over the moduli space is traded by discrete sum instead of a continuous integral, even at finite lambda. So on the one hand, this suggests that maybe there might be a direct finite lambda analog of what Rajesh Matthias is doing, are doing, which basically shows that there is some localization happening, and then like modular integral is localized at. But their analysis is just for tree level or free mills. But integrability analysis suggests that maybe something like that could also be true at finite coupling.
Will this discrete sum become an integral in the limit lambda goes to infinity?
If you take lambda go to if you send lambda go to infinity and L over square root to lambda fixed, then this becomes like a continuous. But just lambda going to infinity is not enough. So if you consider Konishi, then we don't expect that things become continuous.
I see.
Is that related to the flat space limit? Is there some flat space limit?
This is not the flat space limit. In the flat space limit, I think we want to take L finite and then lambda infinity. Yeah, this is more like a BMN or.
So the the difference with BMN is all the L's are in the same direction.
Right.
Is that true for you also?
No. So that's another point. So another important point is to really understand hexagon from some kind of gauge fixed worksheet. We have a formula which is basically hexagon, which allows us to also compute the strong coupling quantities, but we don't know how to derive it from worksheet. And the weird feature of hexagon is that, so let me just draw hexagon again. So let's say we want to compute the 3-point function of some operator, which are at different positions, O0, O1, and O infinity in n equals 4 supermills. And that is given by this, and which can be decomposed into hexagon.
So do you want to think of this as left and right movers on the world sheet?
Oh, This hexagon and this hexagon. No, I think it's different from left and right mover because this is really geometric splitting of the worldsheet.
I mean, you're cutting open the closed string, right? And you're making it, I mean, it looks like KLT type, right?
Okay, that I agree, yes.
And KLT looked like a chiral half, right? And the open string looks like the chiral coordinate.
That's true, yeah. But I think it's not, well, at least I don't see a direct, like a relation with this one to be left.
This is really just cutting the thing in half, right?
Yeah,
It's
cutting
not
it to half.
Like,
Well,
it's
it's
really holomorphic and anti-holomorphic.
Right, I mean, isn't it like KLT a little bit?
No, so it's like, it's really cutting, so 0 to pi and pi to 2 pi. It's not like,
Yeah, so,
I mean, there are analytic analogues, you know, so Francis Brown has these fancy ways of doing double copy, but it's not completely elementary. Well, this is double copy in some sense.
okay, so let me just finish what I wanted to say. So in hexagon, like each magnons are described in exactly the same language as the language that we use for computing the spectrum. And as I said, the language that we use for computing the spectrum can be derived from the gauge-fixed worldsheet, in which Hamiltonian becomes d minus j, where d is the dilatation and j is R symmetry, and then length of the string becomes j. However, one thing I should note is that whenever you compute a 3-point function in the gauge theory, you are inserting operators at different points, which means that the dilatation around this operator, let's call it dilatation for operator 1, is different from the dilatation for this operator. So because we got natural dilatation for this operator is the dilatation around the origin, whereas for this guy is the dilatation around 1. So in some sense, the hexagon, in order to describe the hexagon, it seems like we need to use different gauges, light cone gauge fixing for different operators. And what hexagon does is to patch together different gauge fixing conditions. And normally, if you do something like that, let's say in flat space string theory, you expect something horribly complicated. Well, at least it's not something natural that you would do. But at least in this context, hexagon is telling us this is the way to simplify the problem. So then the question one could possibly ask is there a flat space analog?
Sorry, but already in flat space, your moduli space integral is very different.
You mean like because it's continuous?
Yes. So it sounds like there would have to be a difference to compensate for that difference.
Right. Yes.
I mean, that problem also you would see the analog of that in flat space, because I mean you would calculate vertex operators that sit at different space-time positions, and then somehow that would.
Yeah. So it should be possible to define an analog of that in flat space, and the question is whether that leads to some simplification, because normally we don't expect that to simplify.
flat space, you certainly have to do continuous modular, right? To get the you have to have continuous modular.
Let me just say one thing. So also in flat space, we can do the, in the honest flat space, it's always continuous. So let's imagine doing the light cone gauge in flat space.
You don't have to imagine people do
Yes, that's true. Yeah. Yeah, I guess especially for you, you don't need to imagine. Okay. But then the length of the string becomes p minus. But instead of doing the light cone gauge in the flat space, let's consider what people often call DLCQ, which is to discretize, the periodize the light cone direction.
Sorry, what does DCLQ stand for?
DLCQ.
Sorry, DLCQ. Discrete light cone quantization.
All right, okay.
Which basically means that you just compactify the light cone direction. And if you compactify the light cone direction, this p minus becomes some integer times some number, integer over r, where r is the compactification radius. And if you start computing the loop diagrams using this let's say something like Mandelstam representation, part of the moduli, well, even in the usual light-cone gauge, part of the moduli becomes like is traded with the integration over P minus.
So are you saying that if we compute a one-loop scattering amplitude in string theory, there is you can write down another formula for the same answer that involves a discrete sum instead of an integral over tau?
Yeah, if you do the DRCQ.
And it will give you the same answer?
You're putting it in a box, that's what you can tell. So if you put it in a box, then
Yes,
you don't
yes.
have holes anymore. So then, okay, so then, but flat space is not in a box. Flat
It's
space
not
is
really
flat.
flat space, right?
No, but later you take this to infinity, right? You think of this as regulator and take it away.
But then the sum becomes an integral.
I was wondering.
That's true. That's true. Yeah. Okay, so I shouldn't upset the flat space, but I just wanted to mean that like if you consider DLCQ, there is a situation in which at least the part of the moduli gets discretized, and in some sense that's kind of what's happening here, because we are using some S5 direction for the gauge fixing, and that's part of the reason why we have a discrete sum.
I see. Of course, if you put a spatial box, if you put a spatial circle, the usual formula is still an integral over moduli space. In that situation, can you find another formula for the same amplitude which has a sum?
That's a very interesting question. Yeah, that's a very interesting question. Maybe something like static gauge might do the job.
So this is why the Netzier formula works, because it gives you the poles when you do the integral.
Oh, I see. Yeah, okay, I see.
Right, exactly. We don't need to go to one loop, just four graviton scattering. Yeah. Okay, good. I mean, if you could just write down a formula, you can derive another formula for the Venetiano amplitude that comes not from an integral but a sum. I think that would be a dramatic development.
Yeah, I agree. Okay, so but since lunchtime has started already, so let me just end here.